All the parameters or statistics we have seen serve the purpose of evaluating data within a sample or a population. For example, with the standard deviation, we can evaluate how data values vary about the mean for samples or populations. But it is also of interest to evaluate how much means of samples of equal size taken from a given population vary from the population mean. This is where the sampling distribution comes in. Imagine you're at the cinema and the movie's exceedingly boring. Luckily, you have bought a huge bag of popcorn and decide to measure popcorn grain sizes, well, because you're the type of person that always totes a measuring tape. You take grain size on a first sample of 30 random pieces of popcorn and you end up with a mean of 1.21 centimeters. You put back all the popcorn pieces into the bag, shake it up, and take another sample of 30 pieces, and you end up with a slightly different mean of 1.17 centimeters. You can do this again all over and over, and then you end up with, say, a total of 100 samples. Now what you have is an actual distribution of sample means. This is also known as a sampling distribution of means. Now your mean of your means is actually equal to 1.09 centimeters, which actually is the same as your population mean of 1.09 centimeters. Now, more precisely, a sampling distribution is a distribution using the means computed from all possible random samples of a specific size taken from a population. Note that you can have a sampling distribution of any statistic, may it be the standard deviation or a chi-square or anything else you can calculate. Going back to our sampling distribution of means of popcorn sizes, we can notice how our means are not actually equal and can be slightly different than the population mean. These differences are due to the sampling error. And the sampling error is the difference between the sample measure and the corresponding population measure due to the fact that the sample is not a perfect representation of the population. Sample distributions of means have specific properties. The first one is that the mean of the sample means will be the same as the population mean. Let's do an example to prove this. Imagine you have rolled the dice 6,000 times. We'll assume this will be the population. So our frequency distribution is actually like this. You'll get 1,000 times each one of the values of the dice, and your mean would be 3.5. Now, by taking samples of 5 values from your population, you can end up with many different samples. For example, you can end up with these 2 samples. Each of these have a mean of 3.6 and 2. If we take the mean of our 2 means, we end up with a mean of 2.8. Now, if we add a third sample to this that has a mean of 2.4, our mean of means is now 2.67. With a fourth sample, we end up with a mean of 3.8. Now our mean of means is actually 2.95. And if we take another sample, we have with a mean of 4.4, our mean of means is 3.25. And then yet another sample with a mean of 3.8, our mean of means is now 3.33. Eventually, majority of your samples will have a mean around 3.5. You'll also have samples with low means and very high means, but most of them will have a mean that is around the population mean. So if you do this enough times, your mean of means will actually be the mean of the population. To do a full demonstration would be too long to do here, but feel free to try this at home. The second property of the sampling distribution of means is that the standard deviation of the sample means will be smaller than the standard deviation of the population, and it will be equal to the population standard deviation divided by the square root of the sample size. Well, you'll agree with me that this is a rather long statement, so we'll split it in two and start with the second part. It states that the standard deviation of all our sample means is equal to the standard deviation of the population divided by the square root of the number of values in our samples. This comes from this equation, which is actually the variance of our sample means is equal to the population variance divided by the number of values in our samples. We could prove this mathematically, but it is outside the scope of the class. But we do know, though, that the standard deviation is nothing more than the square root of the variance. So by square rooting the second equation, we come back to our original equation. Now, saying standard deviation of the sample means is rather wordy, so we can replace that simply by standard error of the mean. The first part of the property makes sense when you stop and think about it. The vast majority of the means you will calculate will be well within the range of your population. So by default, the range of your sampling distribution will be smaller than the range of your population. This will also be reflected in your standard deviations. Even more interesting, though, is the fact that the larger your samples, the smaller your standard error. Remember that the mean is very sensitive to extreme values, especially when the n is small. As such, when your samples are very small, you have a greater probability of getting very high or very low sample means, which will give us a more spread out distribution of means like this. Even so, our standard error will still be lower than the population standard deviation. Now, if you take samples from the same population but with a higher n, say 20, your chances of getting extremely high or extremely low means is lower, so your distribution of means will have an even lower standard error. Notice, though, that there are still extreme values in this second distribution of means. Continuing with this same logic, if you take samples that have a very high n, like 100, you need a lot of extreme values in your sample to have very high or very low means. As such, your sampling distribution of means will have a much smaller standard error. There is a third property for the sampling distribution of means, and it states that as the sample size increases, the shape of the sampling distribution of means will approach a normal distribution. This is called the central limit theorem. So no matter the shape of your population distribution, if it looks like this, or even like this, your resulting sampling distribution of means will closely resemble a normal distribution. Because of the central limit theorem, we can answer questions about sample means the same way that we use the standard normal distribution to answer questions about specific values by using the z-score. For example, we could ask ourselves, what is the probability that my sample mean is lower than 42% of all the possible samples? Or, if I select a sample with an n of 40, what's the probability the mean is between 2.3 and 6.7? We must use caution, though, because the z-score equation we used previously is not quite adequate in these types of scenarios. Indeed, we must use instead this equation, where z is calculating by taking our sample mean, to which we subtract the population mean, and then divide the result by the standard error, which is the population standard deviation divided by the square root of the sample n. Let's do an example. The average annual Canadian consumption of red meat is 62.9 kilograms per person. Assume a standard deviation of 7 kilograms and an approximately normal distribution. Now, if a sample of 40 individuals is selected, find the probability that the mean of the sample will be less than 65 kilograms per year. So first, we must sketch what we're looking for. We're looking for the probability of picking a sample that has less than 65 as an average. And then we must find the z-score for this, so simply by changing the numbers, we get to a z-score of 1.90. So 1.90, the area to the left of that z-score in the z-score table, is 97.13%. So we have a 97.13% chance of getting a sample with a mean that is lower than 65. Now it's your turn. Assuming these are the car maintenance costs in Canada, what is your chance of getting a sample with the N of 30 that actually has an average car maintenance cost that is lower than $4,750? The answer is 1.36%.